Let's begin by doing a quick summary of periodicity by discussing the periodic table. So the periodic table is made up of rows and columns of elements listed by increasing atomic number. We start with element 1 here, 2, 3, 4, and so on. The rows from left to right are called periods. We have 1 through 7. And the columns up and down are called groups. We have 1 through 18. One way that the periodic table is divided is into metals, nonmetals, and metalloids. You can see in this blue color most of the periodic table, and everything on the left here is metals. The top right corner in yellow are nonmetals, and a few elements that we see on this little stair step here are called metalloids, or you might also see semi-metals. And these are elements that have properties of both metals and nonmetals because they're right in between the space that divides them. Remember that the periodic table is arranged into columns or groups. Those groups have names that you see here. The alkaline metals, group 1, alkaline earth metals, group 2. The middle D block of the periodic table are known as the transition metals. The oxygen group, the group that starts with oxygen, is often called the chalcogens. Group 17 that starts with fluorine is the halogens, and group 18 are the noble gases. Elements are arranged into these groups with similar reactivity. How an element reacts depends on how its electrons are arranged. Elements that are in the same group with the same chemical properties have very similar electron configurations. Here's a summary of the periodic table groups along with their characteristic reactivity and electron configurations. So group 1 alkaline metals have a S1 ending and are very, very reactive. Group 2 alkaline earth metals have an S2 ending and are very reactive, quite reactive but less reactive than an alkali metal. The transition metals, the D block, have an NS2 and then N-1, whatever this N is, -1, D ending. Transition metals are somewhat reactive. They're what we think of when we think of typical metals. The inner transition metals, the F block that we often see down below, have an NS2 and then whatever N is, -2F, right? So if this is 5S, well, let's see. If this is 6S2, then this would be 4F, right? Somewhat reactive. A lot of those inner transition metals in the F block are radioactive. Then group 16, the chalcogens, that's the one that starts with oxygen, have an S2P4 ending. They are very reactive to the alkaline earth metals. So like oxygen is very reactive to something that's in group 2. The halogens, group 17, S2P5 ending, are highly reactive. The noble gases in group 18 have an S2P6 ending and are non-reactive. We often call those the inert gases because they are not very reactive. Before we begin talking about the trends that we might see in the periodic table, let's discuss effective nuclear charge. Effective nuclear charge, or ZEFF, is the amount of charge that the outer electrons actually feel from the nucleus. The nuclear charge that an electron experiences depends on both the attraction to the positive nucleus and the repulsion from other electrons. For example, in the sodium atom, the 10 inner electrons prevent this one valence electron from feeling the full attractive force of these 11 protons in the middle. So let's go through this. There's one valence electron. There are 11 protons in the nucleus. This attracts the valence electron with a charge of +11. However, there are 10 inner shell electrons. These repel this valence electron with a charge of 10-. The effective nuclear charge, therefore, on the valence electron is the difference. The attraction from the nucleus plus the repulsion from the inner core electrons, which gives us a total effective nuclear charge of +1. The effective nuclear charge is equal to the number of valence electrons. So, what is the periodic trend in atomic radius? Across a period from left to right on the periodic table, the effective nuclear charge increases while the energy level remains the same. Electrons are being added to the same outer level, where the protons are added to the nucleus as the atomic number increases from left to right. The force of attraction between the nucleus and the valence electrons, therefore, gets stronger. Valence electrons are pulled in tighter, the electron cloud gets smaller, so the radius gets smaller. Down a group, the effective nuclear charge remains the same while the energy level is increasing. An increase in energy level expands the electron cloud. The increased distance from the nucleus to the valence electrons makes the force of attraction decrease. Electrons are not held as tightly, so the radius gets larger. Here's a visual representation of the trend in atomic radii. As we go down a group, the atomic radius increases as we're adding an energy level each time. So the distance from the nucleus to that outer energy level increases. The electrostatic attraction decreases and the atomic radius increases. As you go left to right across the periodic table, what's happening is the effective nuclear charge is increasing. The electrostatic force of attraction between those outer electrons and the nucleus is increasing, pulling them in more tightly, decreasing the radius. Okay. Generally, you can see that the trend goes largest from here, and then as you go to the top right of the periodic table, the size decreases. What about ionization energy? The ionization energy is the amount of energy required to remove an electron from an atom. Removing an electron creates a positively charged atom called a cation. The first ionization energy is the energy required to move the first electron. So I have a calcium atom shown here with 1, 2 valence electrons. If I remove the first electron, I have a calcium +1 charge plus this free electron. Now this second ionization energy is the energy required to move the second electron. So if I take that positive ion and remove a second electron, I get calcium 2+ and then that second electron. This continues for third ionization, fourth ionization, and so on. As we know, across a period, the effective nuclear charge increases and the force on the electrons increases. This makes it harder for an electron to be taken away. The more tightly those electrons are held, the more difficult it will be to remove them. Down a group, the effective nuclear charge stays the same, but remember that down a group you're adding energy levels. So the radius is much larger, which makes the force of attraction less. It is therefore easier to take electrons away because they're less attracted to the nucleus. So as you can see, first ionization energy increases across a period from left to right and decreases down a group from top to bottom. And again, generally from the bottom left corner, ionization increases up to the top right corner. Electronegativity is a measure of the tendency of an atom to attract a bonded pair of electrons. The atom needs to be a part of a molecule covalently bonded. Electron affinity is defined as the change in energy of a neutral atom when an electron is added to that atom to form a negative ion. In other words, the neutral atom's likelihood of gaining an electron. Most of the time, the atom results in more stable configuration by adding electrons, and the energy is negative. There are subtle differences between the two, but both follow the same trend. The effective nuclear charge is the main force in attracting the electron to the specific atom. Let's take a closer look at electronegativity. Going across a period, the effective nuclear charge increases and the force on the outer electrons increases. Because of that, it is easier for the atom to attract additional electrons. So electronegativity increases. Going down a group, the radius increases. Therefore, the force between the nucleus and its electrons decreases, and it's harder for that atom to attract then even more or other electrons. Electronegativity and electron affinity increase across a period, and we can see electronegativity here increase from left to right in general, and decrease, we can see decreasing down a group. Metallic character is another periodic trend. The metallic character of an element is a measure of how loosely it holds onto its outer electrons. Remember that for a metal to conduct electricity or heat, it needs to have electrons that are free to move throughout it, not tightly bound to a particular atom. So, the metallic character of an element then is inversely related to its electronegativity. The stronger an atom holds on to its electrons, the less metallic it will be. So, on the periodic table, metallic character increases as you go from right to left across a period and from top to bottom of a group. Properties of metals include good thermal and electrical conductivity, high melting and boiling point, shiny appearance, and malleable and ductile nature. We can see that trend here, that metallic character increases from right to left and from top to bottom. Again, just like every trend, we have greatest metallic character in the bottom left, and that decreases as we head toward the top right. And this one is pretty straightforward if we remember the separation of the periodic table into metals, nonmetals, and metalloids. All right, what about the periodic trend in the size of ions? Let's start with cations. So we see a bunch of metals here from groups 1, 2, and 3 that form cations. In gray is the neutral atom, and in pink is the ion, the cation. Cations are smaller than their parent atoms. You can see that in every case here. The more electrons that are removed, the smaller the cation becomes. So these +3 cations are a lot smaller than their parent atoms. When the outermost valence electrons are removed from an atom, there's an increased nuclear attraction for the fewer remaining electrons. What about the sizes of anions? So in gray, again, we see the neutral atom of several nonmetals that form anions from groups 6 and 7. In blue, we see their ions, so oxygen 2-, fluorine -. You can see that anions are larger than their parent atoms. The more electrons are added, the larger the anion becomes. With a greater number of electrons, the effective nuclear attraction is less, and there is more electron-electron repulsion. So the electrons in the outer shell are repelling each other more, causing the radius to increase. In general, across a period, cations decrease in size just as atoms do. Similarly, anions decrease in size left to right across a period for the same reason atoms do, increasing nuclear charge. How might we put an isoelectronic series of ions in order of atomic radius? So in an isoelectronic series, ions have the same number of electrons. So for example, here, sodium +1, magnesium 2+, fluorine -1, oxygen 2-, and neon all have the same number of electrons. They all have 10 electrons. But they have different numbers of protons. Oxygen 8, fluorine 9, neon 10, sodium 11, magnesium 12. So we have even numbers of electrons, or in other words, the same electron configuration. That's what isoelectronic means. An increasing number of protons. Well, what happens here? Well, the size of the ion decreases with increasing nuclear charge. The smallest ion in this series is magnesium because it has the most protons with the greatest attractive force to pull in the 10 electrons.